Welcome, everyone. This is the second date of SIGGRAPH 2021. We are thrilled to join the fourth session of the retrospective program. It is the first attempt within the SIGGRAPH conference to have a program devoted to the history and legacy of computer graphics and interactive techniques. As the conference progresses, there are many links between the nodes that are the panels. Yesterday morning, in the conversation between Ed Catmull and Pat Hanrahan, there were some mentions to the work of Jim Clark, the legacy of Silicon Graphics, to actually the work that it's credited to both Jim Clark and Ed Catmull, the Catmull-Clark subdivision surface. Many people mentioned that in the Discord channel. This morning, for instance, we had a panel dedicated to the museums, collections, and institutional challenges, with institutions collecting the material culture of computational media. And the first presentation was about the influence of Silicon Graphics machines in the work of European pioneers of the media arts. So this is very moving because we see that there are like connections between the content of the panels, and we are talking about the same history at the end of the day. We're extremely excited to have this panel now. We have the participation of some pioneers, and also we're excited because this is a collaboration between the Computer History Museum, Marc Weber, actually, and SIGGRAPH to join efforts in the discussion about the legacy of the computational history. In this case, in this particular case, the legacy of the Silicon Graphics software and hardware. So Marc Weber, it's one of the curators of the Computer History Museum. He's an expert on the history of the web, and he's been very active documenting, the computational history in general, with several fantastic interviews, as one that he has with Jim Clark that is available in the Computer History Museum website. One thing that is very important is that thanks to the arrangement between SIGGRAPH and the Computer History Museum, this talk will be available soon after the conference, in a couple of weeks. So before the conference closes, this will be already available. And with not further ado, Marc, please take the stage and introduce our fantastic speakers this afternoon. Thanks for joining.
Welcome. I'm Marc Weber, Curatorial Director of the Internet History Program at the Computer History Museum, and I'm truly honored to moderate these amazing speakers. I want to thank Andres and SIGGRAPH for putting together this historical track and for inviting CHM and myself to co-organize this presentation on SGI's pivotal role in transforming not only graphics, but perhaps we'll see potentially aspects of computing itself. So SGI, Jim Clark created what is effectively the first GPU with his students, including Kurt Akeley, who is here. And they went on to found Silicon Graphics, which led the field and helped develop it into its modern form. Julian Gómez is a pioneer and practitioner who played key roles on QuickDraw 3D for Lego and for many others as a consultant, and has been an SGI user and customer since the start. So, and all of the panelists have deep SIGGRAPH connections. So I'll start by giving a little background on the museum and my own work. Julian, if you could roll the first slide. So we have the largest general collection of computing materials in the world. Only 40% is physical objects. The rest is documents, data, software, images, etc. And 35,000 square feet of permanent exhibitions, including some of the main ones on the development of the online world. We also have a graphics gallery and a gaming gallery, which are quite relevant, as well as exhibits on World of Warcraft and a number of other special areas. And we have an oral history program with over 1,000 in-house and hundreds collected from elsewhere. And the Internet History program, the next slide, is basically, I started that in 2008, and we collect the history of the online world, including multimedia and mobile. And I am, oh, and sorry, the next slide, please. And of course, our biggest artifact is the museum itself, which was, and Kurt might correct me, but I've been told the sales headquarters for Silicon Graphics. And then on the right, you'll see some of the Silicon Graphics material in our permanent exhibition Revolution. And of course, we have many machines in the collection. So if we could turn to Julian to introduce yourself, and you have a little bit of background on the setting for where Silicon Graphics came from and what it did.
Right, and by the way, Marc, I really like the fact that you are recursive and that your building is itself an artifact. So I was asked to make a few comments about what led into the existence of SGI. And I want to mention, the first thing to bring up is calligraphic displays. The idea of controlled line drawing by some kind of host has been around for a long time. There was some really good stuff at the panel this morning about the early efforts in the 1950s to do calligraphic displays. Basically, it's a fancy word for drawing lines. When it comes to 3D graphics, though, this creates problems because there's no hidden line removal, which means we end up with optical illusions in trying to do 3D graphics. This has been combated with mechanisms such as perspective, motion, line intensity, and eventually it gave way to the SGI workstation, where the problem just simply went away because nobody uses calligraphic displays anymore. The overwhelming emphasis on most calligraphic systems was interactivity. And as was mentioned at the panel this morning, the idea was that somebody could do something and in real time the system would respond. So they were interacting with it, as opposed to a storage tube where the image was placed on the screen and then it stayed there until the screen was erased. This is a shot from a Tektronix 4014, which many people in the graphics business cut their teeth on. As you can see, it's just lines. The screen had to be erased by flashing it. So for somebody who was using it, you would see intermittently these bright flashes as the screen was cleared. By the mid-70s, Evans and Sutherland had taken the lead in creating calligraphic systems. The picture system 2 here was the Cadillac of 1977. This photo is from the JPL Computer Graphics Lab. And you can see the cabinet on the lower right, that is the picture system. There's a CRT, that's just the monitor. The other square CRT is from the frame buffer I'll get to in a few seconds. And then the two smaller CRTs are just terminals. Now, as I said, ENS was the best. There were many companies doing calligraphic systems such as Adage, CDC, IBM, Tektronix, Vector General. So they weren't the only game in town. The other thing I need to mention is that when I say PS2, it has nothing to do with Sony. We're talking Evans and Sutherland here. The other way of displaying things was a frame buffer, and these came in two types. But the idea was that you would have an image stored digitally, and in a random access frame buffer, you'd store lots of values, which would then get converted to video. This was what we generally think of as frame buffer today. An earlier technology called run length encoding used much, much less hardware because memory was very expensive. But then
Julian, sorry to interrupt, but we are not, you're not sharing screen, I think.
How did?
So if we can go back, because this seems to be very, okay, now we can see.
Okay.
You can go back, no problem. We have time and
okay.
Thank you, Julian.
So let's see. So this chart overall on the left side, as I was saying, goes back to the 1950s. We're starting with the calligraphic displays. And in the 1970s, we started to see random access frame buffers. So the storage tube, as I said, this is, you would put the picture on the screen and it would stay there. And as you can see, it's line drawing. So that's all you get, no color. And then you would flash the screen in order to erase it. So if you were working in the same room with somebody else, you can see these flashes as the room got illuminated. And here is the picture system, which I called the Supreme System of 1977, the PS2 that Evans and Sutherland made. The PS2 itself is that cabinet on the lower right, and the hulking thing in the middle, the CRT display, that's just the display. The PS2 had a very high bandwidth, something like 18,000 vectors a second in real time. So it's also very high quality imagery. The square monitor to the right is the ENS frame buffer, which I was starting to describe. The other two are the text terminals, which were used for programming things because the only input to the system was text. There are some some interaction devices on the counter, and in the middle is one of those thingies called the rotary dial telephone, which you may have heard about from our ancient past. So frame buffers came along. Random access frame buffers were much more popular because they were so much easier to deal with. You know, in the 70s, memory was hugely expensive, so this wasn't really very common. What was more common was the run length encoded frame buffers, but those took lots more circuitry and much more sophisticated lower level programming. By the end of the 70s, we started to see these smart frame buffers where you would give it an opcode and it would then rasterize it. For example, you'd say, draw a circle, and it would figure out the rasterization of the circle and put that into the frame buffer. Some companies making frame buffers at the time were Evans and Sutherland, AED, Grinnell, and De Anza. And there were also some domain-specific frame buffers, such as for flight simulators. As the microprocessors came along, especially the 68,000 series, we started to see the opportunity for workstations, and this is about when SGI became possible. So SGI was a workstation, and some others in the business were Apollo. Sun Microsystems and Symbolics came along a little bit later. And this slide, given the topic of the panel, this slide stops in the 1980s because obviously there's been much progress in the intervening time. At this point, I'd like to switch to a meeting at the Rand Corporation in the late 70s when Dr. Clark announced that he had put the picture system 2 onto a chip. And as you recall, that hulking monstrosity in the photo I just showed, the idea of that being on a chip was really alluring to everybody. This meeting was held at the Rand Corporation in this building visualized by Mike Warman. This building no longer exists, but it was a pretty impressive meeting. Did that show up? Does this visualization show up?
No, I think can you try again, please? I think you need to share the entire screen if possible. Yeah, now we can see. Perfect.
Okay.
Thank you.
So going back to preservation, you know, as I said, this building no longer exists, and but that was where the meeting was held. Now back to in terms of my own experience with the SGI, so I started at the JPL Graphics Lab using Evans and Sutherland equipment, and then at Ohio State using more Evans and Sutherland equipment. The PS300 was a major departure from the previous architecture of the PS2, going away from display lists to a data flow approach, and it was great. After graduating, I went to digital arts using the SGI 1000, the first workstations, and this is when I discovered my first SGI bug, which was that MEX, which was the windowing system at the time. If you gave a MEX window a negative Y coordinate, it would actually completely crash the workstation. So I just wanted to mention that. Then went to NASA using a mix of ENS equipment and SGI equipment. This was about the time that scientific visualization and computational physics were getting really, really hot. And this was the focus of what I was doing and needed the capabilities of both kinds of systems to do that. After NASA, I was working at GBA, a multimedia company using the then SGI workstations and getting a real feel for them. and then went to Lego, where it had everything SGI made. I mean, we went everywhere from India up to the biggest reality monster that was in Northern Europe. Just in my group at Lego, I had a dozen workstations. Overall, in the division at Lego, we had over 60 SGI stations, and just racks and racks of equipment and big cabinets sitting beside each person's desk. And then I wanted to make a couple of comments about software, because in the early days, when you would write some code, it would work only for that particular device. As you can see, the Evans and Sullivan picture system library evolved and had influences on the design of GL and so on. However, in the mid-70s, it was realized it'd be good to have software that worked on more than one system, and SIGGRAPH had this effort into developing the core and GKS standards. And then later on, FIG standard, which actually did become an ISO standard. In the mid-80s, as I mentioned, scientific visualization was becoming a hot topic, and there were efforts at standardizing those approaches to visualization, AVS and APE, and then also I don't want to forget HOOTS. Finally, I need a couple of seconds to be legal for the attributions. And then that is an introduction to my experience with SGI.
Great. So I want to welcome Jim Clark, who has just joined us. There were some logistical issues with the link, and welcome.
Thank you.
So we were going to ask Kurt to give just a couple of minutes on his background up to the point of meeting Jim and SGI.
Great. Okay, sure. I born and grew up on the East Coast of the US in Delaware. I think I was probably born an engineer. I spent the whole time growing up through high school figuring out how things worked and then building as many of them as I could figure out how to build: cars, boats, model planes, radio control planes, the whole thing. Got to the University of Delaware, and after a brief foray in physics, settled into electrical engineering and ended up building a laser printer, one of the very first laser printers as a sort of thesis project with the guy who ran the department, who was an ex-Xerox guy. And on the strength of that, ended up at Stanford in the PhD program, and was very, very confused because there were like 50 or 60 faculty, and I couldn't find anybody who wanted to build anything. And I was, and then I was sitting in a 1-credit seminar course, and that Jim was heading up, and the speaker didn't show, so Jim made a pitch about what he and his students were doing, and I introduced myself, and that's how we got going. I found someone who wanted to build something.
So Jim, if you could give us a couple of minutes on your background up to the point of starting with the geometry engine and meeting your students.
Great. Sorry, I got a little late joining. I had a little technical difficulty. I'm not very good at this kind of stuff. Basically, prior to landing at Stanford in 1979, I had been through the Navy and eventually studied physics for a master's degree and got a PhD at the University of Utah, a famous place at the time. And I landed at the University of California, Santa Cruz, where I taught for 4 years. Then I went out and joined briefly Ed Catmull at New York Institute of Technology. He and I did a few things together, and then I came back and joined the faculty at Stanford. A couple of years later, Kurt, I suppose it was around 81, right, Kurt, or 80?
Yeah, late 80, early 81.
Yeah, so Kurt showed up and showed me this document, which as I read it, I realized that it had been printed out on the laser printer that he was describing in the document. And I thought, well, no, there's a guy who can get stuff done. And Kurt was one of a group of guys that joined us, and Marc Hanna was another significant person there, Rocky Rhodes, Tom Davis, a number of people who started Silicon Graphics with me. And that's sort of it. That's how we got started.
And so where did the idea for the geometry engine come from? The realization of what VLSI could mean for graphics?
Yeah, my first summer at Stanford, I spent some time at Xerox PARC, and Lynn Conway taught a course in integrated circuit design. I picked up on that and was armed with a little bit of knowledge about the so-called clipping divider that Ivan Sutherland and Bob Sproul had worked on. I knew that you could do some binary shifting. It was a very primitive idea, and I thought, that would be a clever way to implement a floating point unit. And then as I thought about it more, it would be a clever way to lay them out in parallel and add microcode to create a complete geometry pipeline. That idea occurred to me on a backpacking trip in Yosemite. And what can I say? It's just one of those things you're walking along and say, oh, that might work.
And so then tell the sort of how you assembled the band of merry students.
Right. Well, there were, Tom Davis had been a good friend of mine from some extracurricular activities that we were involved in, and had just gotten his PhD in math. So I got him involved to help work on some of the software design, and he and Rocky kind of began the software design. Marc Hanna and I did the integrated circuit design of the geometry engine, and Kurt and Mark Grossman did the hardware design around that. And we built a prototype there at Stanford. And as we're reaching the conclusion of that, I began to think it would be a nice idea to try to start a company. And once the other guys agreed to join me, I recruited a couple other people who were more business-oriented people, marketing, manufacturing. I knew absolutely nothing about how to start a company, but I wrote a business plan based on the Stanford Business School, kind of a generic how to write a high technology business plan that I picked up at the business school. And I began to circulate that, talking to a couple of venture capitalists. I spoke to Sequoia, Pierre Lemond, and Don Valentine. And I spoke to Mayfield Fund, Grant Heydrich, and Glenn Mueller. And I spent a fair amount of time, or we, the management team, spent a fair amount of time trying to convince them that we might be able to be successful at doing this. They were not overly convinced, but finally Glenn Mueller decided that he would he got Mayfield Partners to put in a small sum of money, and we were off and running.
And Kurt, could you talk about kind of the feeling amongst the group of students and what the different roles were? And I'm a little, where did you came in after Marc Hanna, but where in the order?
Yeah, sure. After I showed Jim that document, and I became his student nominally, but that following summer, the summer of '81, I was a research assistant for him, and I dutifully showed up, and no one was around. And I think Jim, I don't know if you wouldn't recall, but I think for the first 2 weeks I was your research assistant. I didn't see you. You and Marc were off working on this geometry engine. So I went to somehow got some idea. I went to the computer science library and picked up a copy of Newman and Sproul's interactive 3D graphics book and taught myself graphics. And then eventually I did get to chat with Jim, and he asked me to do a VLSI kind of design for the rasterization backend for this geometry engine. So I had to find out what this geometry engine was. And I spent the rest of the summer doing that. And toward the end of the summer, made a little pitch to Jim and Martin Newell, I think, and successfully. And Jim kind of sidled up and asked if I would be interested in starting a company. And I answered pretty quickly, yes, which I guess was a pretty big risk for someone who'd gotten into a Stanford PhD program, but it turned out to be a really good choice. So that's my short story for how that all happened. I honestly don't know the others. I mean, I think Rocky came out from the Midwest and made a similarly difficult decision, but I don't know exactly how he did. I remember his wife Diane sat in that ERL building with us every evening while we were working away on wire app boards and doing the things we were doing later on, and you know, so it was a pretty close group.
Yeah, I can add a little color to that. Rocky had gotten, I believe he'd gotten a master's degree at Purdue.
Yeah.
And he came to get a PhD. And I think we all came together rather quickly. with the exception of Marc Hanna joined me fairly soon after I joined Stanford. And he and I worked pretty intensively on the integrated circuit aspect. He was mostly writing or he and John Hennessy, who ultimately became the president of Stanford, but John was an assistant professor at the time, and John wrote a microcode compiler for us. And I spent a lot of time writing microcode, and Marc spent a lot of time debugging the integrated circuit design. And then we had a simulator, and we were simulating this thing on DEC computers, I suspect, because that was about the most powerful thing we could find around there. And so we spent a lot of time doing that, at least a year and a half, 2 years before we were getting ready, got it fabricated, and had enough chips to at least build a proof of concept. And around that time, I got Kurt involved because he had obviously been a good hardware designer. And Mark Grossman I had known from, he was a student of mine at the University of California in Santa Cruz, and had done his master's thesis under me in computer graphics. And I seduced him to come up and join us as one of the, just people working on the project. He was paid under the DARPA funding that by this time I was principal investigator for, after Forrest Basket left Stanford. And then David Brown was another person who I don't recall exactly how we met him, but he was around involved in this. And that was sort of the motley crew, as I recall. There might have been one other that ultimately put it together. They were working on the hardware and the system, and I was working on trying to get financing. Of course, once we got financing, we moved out of Stanford, and all of them left. Well, those who were working on PhD programs, I guess it was Rocky and Kurt, and who else? I don't know, but they abandoned their PhD program for the moment and came out and started the company. And then we're really, frankly, it was quite as I recall, Sun Microsystems was just getting started around that time, and I was it's my nature to be extremely paranoid, but I got extremely paranoid about Sun once Bill Joy joined them. And then I set about trying to recruit a bunch of people from Bell Labs who were obviously should have been experts in System 5 Unix. At that time, Berkeley was not licensing the Berkeley Unix, or either that or Bell Labs wasn't allowing them to, because it was based on some, I don't remember the details, but we decided to go down the System 5 path and add networking to that. And BSD, of course, part of what made it BSD was the fact that it had networking implemented and sort of envisioned by Bill Joy. So almost immediately we went from being what I originally thought of as being a terminal company to a workstation company, obviously based on Unix. And we licensed from the Sun project at Stanford. We licensed from Andy Bechtolsheim the original Sun CPU. And I spent a great deal of time trying to get someone to port Unix to our environment. And eventually Kip Hickman joined us. I don't know how he came to be an employee, but he was the kind of systems guy who was willing to, a lot like Kirk, dig in and get things done. And he was, not that the Bell Labs people weren't, but they were all, they weren't quite that type of people. You know, there's a special kind of person that digs into the bits and bytes and makes things work at a detailed OS level. And Kip was one of those people. So he got it running for us.
And was Stanford fine with you guys going off and doing this? Because I know with Cisco, obviously, there was a lot of tension, and Sun and Google, there were considerations. Was it smooth sailing for that?
Stanford was very lenient at the time we started this. Andy took the original Sun design that was developed under the DARPA funding and licensed that. I don't know what details Sun negotiated in order to take that, but I had applied for a patent on the geometry engine, and Stanford gave us a paid up license, basically. They were very lenient. They were very happy. At least they never expressed any dissatisfaction. We're off. I don't recall ever having any difficulty with Stanford. Now, Google was a very different thing, as you probably know. Google, everything was developed right there at Stanford, and Stanford got a piece of Google, and John managed that piece of Google, best I recall. And to this day, he's the chairman of the board of Google. So Stanford made a lot more out of Google than most other companies that left Stanford.
Yeah, there's a complex history of spinoffs, mostly very, very successful. And VLSI early on was, I mean, now of course it's assumed, but I mean, Julian had talked about people needing some convincing early on. Kurt or Jim, do you want to talk about how was it perceived?
Let me make a comment, because I know Kurt will chime in. VLSI, as was done on the geometry engine, was never really used at Silicon Graphics. Instead, Kurt, working with, I don't know who else, he'll tell you, but I know TJ, Tom Dermelack, and Kurt were pretty adamant that we build a system using more conventional approaches, not full custom integrated circuits. And we never did go to market with any kind of full custom circuits, but semi-custom, I guess you could say, gate arrays and control systems. But before I say, I want to mention Kurt. I had forgotten, had mentioned Martin Newell, and he's a really important person in the sense that Martin more or less was the genesis of what we call GL, the graphics library. It was more of a set of routines that you call inline code, and I used it. I used that approach, kind of a unique programmatic approach, to teach graphics when I taught it at Stanford. And so, to some degree, the GL as we implemented was an outgrowth of what Martin Newell did. And originally he was going to be involved in the company, but he ended up taking a job or joining the company that I had gotten to manufacture the first Sun microprocessor boards. It was a company based in Illinois. And for some reason, Martin, I guess he got impatient. He and I had talked about starting a company for many years, and he got impatient, I think, and joined them. But we then subsequently went ahead and joined him. So I now know what you remember, the meeting that Kurt was referring to, in which Martin was there. But I like to acknowledge Martin personally as one of the inspirations from my days at the University of Utah. He was there.
Maybe I could fill in a little of my perspective of all this. Is that good?
Definitely.
Great. So I mean, the early products, the one Julian mentioned, 1000, there was 1000, 2000, 3000 terminals, then ultimately simple Unix workstations based on 68000s. Those products did actually ship with the original geometry engine. And during that time, or with slightly industrialized, hardened versions of the original geometry engine. And during that time, Marc Hanna and a team were working very hard to bring that same sort of technology to the back end, to the rasterization, to fulfill the stream. And I had been hired to use standard TTL circuits and off-the-shelf stuff and build backends until we got the proper fully parallel backend done. And what was becoming clear kind of 85, 86-ish is we weren't getting the backend done. All of our energy was being consumed just keeping the geometry engine sort of current and up to date. And I looked at the schedules for the stuff. It was taking years. And I remember making a comment one day saying, when I found out that there was like a year of simulation in there, and I said, we could implement these algorithms with gate arrays, and I could simulate it really quick. And then I thought, and we could ship that. so that's, I went off with a handful of people, Tom Jermolak, and then a handful of engineers. And we basically put together a crash program, if you will, to build not just a new type of geometry engine, but also to use these gate array technologies to build a fully parallel back end. Because up until that point, we just weren't realizing the value of the geometry engine. It's not best at replacing a calligraphic system, but all we could really draw effectively were lines. And so until we had a fully parallel back end where we could do hidden surface elimination and some modicum of shading, it just didn't come to fruition. And so that project conceived in '86 at SIGGRAPH 86 in Dallas and shipped in late '87, which was pretty quick for us. I think was a real turning point. Like Jim, you look like you want to weigh in on that one.
No.
Yeah.
I think that's exactly right. I'd forgotten that we actually shipped the geometry engine because I guess I was involved. I certainly wasn't involved in any of the technology at that point. I was trying to keep the company.
That's right. Raj was doing the geometry engine tech.
That's right. But in fact, I don't even remember some of what you said. That's the nature of being 15 years older or whatever.
I'm working on it.
And in terms of like calligraphic, did you think at all about older? Obviously GL became OpenGL, but did you think about, FIGs or older standards? Was there any consideration for the more vector-based things?
Let me comment on the GL became OpenGL. The OpenGL,
well, not became, yeah.
To the best of my recollection, and Kurt can clarify this as well, but Kurt was one of the people, I think the company generally was concerned that Microsoft would define something that would become the standard and we would be left in the backwater. And my recollection is that Kurt took up the project of defining an open standard, which we called OpenGL. And he led that effort as best I recall. Kurt?
Yeah, I did. A way to think of that is that when we started SGI, I was a TTL bits and pieces hardware designer, and the great goal of Silicon Graphics was to do custom silicon design. So I imagined I would learn that and do that. And in fact, it all went the other way. I ended up thinking more about systems and ultimately more about software interfaces. And it turns out, I think that's the right way to think about it. So OpenGL was motivated because of PEX, which was figs in X, which was a competing standard in the workstation market, and the observation that wasn't clear to the PEX people that doing a standard on an X Windows protocol level meant that it would run on about 2% of the machines in the world and leave out the 98% that were Microsoft machines. And so my interest was not doing a standard that would just be cornered into workstations, and certainly not being forced to implement such a standard, which we thought was not as good. But so OpenGL was designed to head off PEX in the workstation market and bring Microsoft into the fold and PCs and in the remainder of the market and become a standard. And I'll just pitch a little bit more. Standard kind of sells it short. I really think the way to think of OpenGL, and this is a little bit of a retrospective way, is to think of it as the architecture of interactive 3D graphics. That the libraries up to that point were not rigorous enough to really call themselves architectures. I think OpenGL was, although it didn't. We didn't use that term, but we were doing all the things that should be done, making sure there were no undefined behaviors, making sure everything was composable, and trying to design a system that would solve problems beyond the ones that we understood at the time. All those things that good architectures do, we set out to do with OpenGL, and largely succeeded. For 25 years, it kind of pulled Microsoft along. We can go into the whole messy details of how that all happened, but the fact is that it did specify an architecture, and that architecture was good for the industry overall. I don't know if it was that great for SGI, but it definitely provided a firm foundation for interactive 3D graphics industry.
Well, I think if we hadn't done that, or if you hadn't done that, we probably wouldn't have been successful, because Microsoft would have ultimately tried to define something. And given their influence, I think they would have brought the world along with them.
Yeah.
And then we would have been kind of a servant to whatever they chose. I've, had more than a few experiences with that with Microsoft.
A lot of people have had more than a few experiences with that.
And I'm also wondering, so looking from the outside in, and maybe Julian could say he's already said some about, but what was the impact of this on the way people actually worked with graphics? I mean, changing from a machine that you share with other people that's tremendously expensive to having it 24/7 on your desktop.
I would say I was working mostly with computer animation at the time, and it tremendously revised the way and design was done. Because see, before that, you could do the wireframes images on one of the line drawing displays. But as I said, there were problems with doing that. If you wanted colors, you could not do color, not interactive previewing. And it was just too expensive to, a flip book coming from the classic animation side. It was just too expensive to render a flip book, decided you wanted to redesign, then render another flip book. So when the SGI came along, people were able to do interactive color previewing of their designs, and it tremendously streamlined the entire design workflow.
Did it actually change jobs and job descriptions? And
probably, because then we ended up with things like wavefront and alias, where you had to become skilled at using one of these more sophisticated animation systems. Prior to that, it was, for example, at Ohio State, you learned how to use the system that Frank and I wrote, and that didn't transfer to anywhere else. But if you were using wavefront a few years later, then you could expect that it would be a skill that you could keep on using even after the authors went away.
And thinking about competition, which, I mean, in the end, no one quite in the same space, but early on, I mean, Apollo and Sun were, I mean, Jim, you talked about being paranoid about it, but I mean, they were calling themselves graphical workstations more in a GUI kind of way for the interface. But I mean, was it clear that they were not going to go into this market? Or, I mean, how did you guys think about that?
Certainly not the way we were. I don't think that even Sun or people at Apollo today would argue that they knew as much about graphics. We developed, I would argue that we didn't have a monopoly on this idea, but we were, as a company and as a company building products that supported the system we talked about, I don't think anyone could, well, no one could quite match it. However, it wasn't at all clear to most buyers that, number one, you needed it. I still remember people saying, why do you need all this 3D graphics in some of our sales concerns? But number two, they just weren't. Sun went to a lower price point. We were very expensive, but it was my perennial frustration was that the company built products that ended up being very expensive, and it obviously the reason was we built all of this extra graphics capability, but it's one of the things that made it very hard for us to build market share quickly.
Yeah.
One comment I have there is speaking from the user viewpoint, although there were different workstations available, SGI was generally the favorite choice because the way they approached doing graphics just made more sense. And this leads into the other point, which is that even though they were more expensive, the decreased productivity from using something else was likewise expensive. You know, if it took an animator 3 times as long to design on some other workstation, that cost money. So it sort of looked expensive.
And the bulk, I mean, obviously Hollywood and blockbuster films were the best known face of SGI, but that's, as I understand, a tiny percentage of the customers. I mean, who were the CAD? I know was big, but who were the main customers?
Well, they kind of ran the gamut. Mechanical engineering, CAD, as you say. There were computer animation people, the visual effects industry, commercials, people doing commercials and special effects for wowie kind of presentations, but short to get attention, as commercials are meant to do. And then, of course, the full-length animation people. I don't recall exactly whether Pixar became a user, because Pixar had built the thing called Pixar as a kind of an image processing engine, kind of the ultimate back end. That
We have one in the museum, actually. On display.
Right.
But I think that ended up essentially. I don't think it went very far as a piece of hardware, but rather the smarts about how to create very realistic looking images that people like obviously Ed Catmull had spent their graphics life inventing and doing, were that eventually the algorithms and so forth. And I think SGI was probably used somewhere in there to help with some of the pre-animation and the real-time visualization of sort of motion sequences. But in the end, each frame in those motion pictures is a complex, time-consuming render. And so the whole idea was to speed that up and make it with movies. And in the meantime, of course, I don't quite know how this coincided with us, but I know that Pixar was bought by Steve Jobs and run independently from what he was doing, and then he joined Apple, and then ultimately it was sold to Disney. So so that was another. And chemistry design, chemical molecule visualization. In fact, I remember getting our guys. It was hard to convey to people in those days. Everyone at SIGGRAPH would know these things well, but in those days, as I said, why do we need all this 3D graphics? And so I asked Gary Tiroli, who was a good programmer and he had written a flight simulator that we used. I asked him and a group of guys to just write an example of manipulating a molecule, write another one of manipulating a 3D car, a 3D mechanical part. There were already ample examples of commercials and the like, but we had to spend a lot of time kind of pushing on these various market segments, all of whom we believed could use this capability. And then, of course, you have to have the applications, the support software, the Wavefront-like software to enable each and every one of those. And so it was a slog. It was actually a lot harder, I suspect, than what Sun encountered by just selling bitmap terminals or bitmap graphics workstations. Sun was more of a copy of what the Xerox PARC people had done in the Alto, I mean, and just as ultimately Steve Jobs did in the Macintosh.
I mean, another way to think of who SGI sold to is we sold to people who dreamed of doing something that they couldn't do. And those people were just floored by the possibility of doing radiation treatment planning interactively, or figuring out why the wings tear off fighter jets interactively, or building a 777 without having to mock one up first. It was the first Boeing plane that actually flew the first one, right? Doing these things was what SGI, especially at the high end, which was where I was more involved, was about. And it was absolutely fantastic. But as a business model, it kind of comes up dry at some point, and when things get commoditized. So it was the opportunity of a lifetime to work with all these smart people who had all these really difficult challenges and figure out how to build systems. And it wasn't just the engineers helped, and we had a whole sales support group that was full of like PhD people who would get the first planetarium that was fully digital. Right. I mean, we didn't just sell them the 7 infinite realities. We pretty much wrote the code for them too. Right. And that was a classic SGI deal. And in order to do that, you had to charge these high margins on big, expensive machines. So people were getting value, right, Julian? I mean, there was real value in it. But then after the pace of innovation dropped even just a little bit, the ability to run that business model kind of, and that's my impression, is it got harder, right? But wow, what a ride.
Yeah, well, Kurt will reinforce, I'm sure, was always a bit frustrated that we were selling very expensive hardware. And so I was trying to get us down market. I don't think I fully got, well, in fact, I know I didn't, because I was pushing us to build very low cost workstations. Personal Iris is one outgrowth of that. And, but even that was a $15,000, $20,000 machine.
It's an expensive low cost work computer.
Right. So, ultimately, it didn't make it. The company spent, I think, through the Forrest Basket, Tom Termelak, Ed McCracken, all of the, Tom was leading the high-end division, so he thought that way. Forrest came from, he had worked with Cray, and he thought that way. And Ed McCracken was far more, I guess, sold by their points of view. I don't mean to blame or attribute that to them. I'm simply saying my recollection was that it was like pushing on a string to try to get the company to move down market. And each year it became more and more frustrated as I began to realize people were building graphics accelerators, they were adopting OpenGL, they were making PCs.
Yeah.
This stuff. And the Intel of the world were lapping us, although I could see it happening. It hadn't happened, but they were going to make the CPU available from the 86 architecture, available to people at a very high performance level at the software. And then there were graphics accelerators going to be able to do what we did with the OpenGL, which we made open. So it was kind of, I felt I saw the writing on the wall. I wasn't particularly popular with Ed McCracken. So I decided, okay, maybe it's time for me to move on. That's what my wife told me. And so I just began to, this was by 93, I was incredibly frustrated. And part of the reason was it was just as clear as day to me that we could not be successful at the high end, only at the high end. We had to have a broadly diversified product line. And I felt the big money was being made at the low end. I didn't see it in the form of a GPU, selling GPUs. But I did see it in the form of price, right? The price point had to get much lower. And ultimately, I don't know that we ever could have succeeded at all, simply because the PC had such strength and momentum going forward that we were never able to develop, and even Sun wasn't able to develop. Obviously, Apollo wasn't. So we all had a great time building the workstation industry, and it was one of the smartest group of people I've ever been around. In fact, I'd say unequivocally, the smartest group of engineers I've ever been around was the group at Silicon Graphics. And that's not to take away many of the people at Netscape or, a company that TJ and I have right now. It's just it was a grand effort and a grand experiment. And I think the internet came along as an alternative for me, and I just said, I'm out of here. But
Before we, go on.
I'm just babbling. Go ahead.
Oh, no, I want to leave just a few minutes for questions. I did want to ask about, in terms of the team, diversity. I mean, Marc is African-American, and in the photo, there's several women in the team. What was the group like in terms of diversity?
I don't think we thought of it in those modern terms. Marc was Marc Hanna, and he happened to be black, but I never thought of that. And neither did Forrest, neither did Stanford. They let him in. And then we had a huge number of Indians. And Eastern Indians, Southeast Asian Indians. And we had a lot of women. I don't recall specifics. Kurt will know a whole lot more than me, but I don't remember it. Diversity as being much of an issue with us.
Yeah. Weren't thinking about it. There were certainly great female engineers, but not by any kind of design. Just we hired the best people.
Right.
And then just a last quick thought. So where do you think the future is going for GPUs now that they're doing a lot more than graphics?
I'll let Kurt answer first there.
Oh, sure. Well, I mean, everyone already knows that if you open up a GPU and took out all the stuff that's graphic specific, it would still look pretty much the same, right? There's the NVIDIA calls it the raster op, the ROP at the back, and there's a little rasterization hardware. It just turns out rasterization works 100 times better if you make a little bit of custom silicon. But after that, it's all a giant parallel processor, and where it's going is to be a more and more giant parallel processor, and it's remarkably successful at doing that. I think the little bits of graphics parts will stay there, but it just gets to be a more and more impressive, highly parallel system, and that's how it comes closer to what people think of as Moore's law in terms of a performance increase per time instead of just a transistor count increase. The microprocessors just can't keep going faster, but an NVIDIA part dealing with the data parallel problem can just keep going.
Yeah, if I can add,
just have 4 minutes left. So if you would like to wrap up and conclude.
Sure. And do we have time to take one or two questions, or what do you think?
There are no questions now, but I think
okay.
Jim was about to say something that would be.
Yeah, please go ahead.
I was just going to reinforce what Kurt said. The idea of having a custom piece of hardware was a kind of a reaction that I got, a negative reaction I got from the people at Xerox PARC, who at the time had just created, the Alto. And there was a general thinking that the CPU was going to get more and more high performance and eventually be able to do all of the graphics you would want, including real-time graphics. I didn't believe that. I don't believe it today. The idea of building a custom piece of hardware that can be used in very specialized ways and specialized tasks is still true, and it's still valid. And I think NVIDIA, who inherited a bunch of our high-end graphics people, have proven that. They built a $500 billion market value company building those things. And by the way, those things are useful for Bitcoin mining, and they're useful for a whole lot of different things that have nothing to do with graphics. So I think that's the way it's going to be as an ongoing thing. I don't see a fundamental change to that kind of architecture. I think there's always going to be a need and a value for having a super specialized little thing. We have specialized eyes. We have specialized ears. And in some sense, that is a specialized engine that makes a great accessory for a general purpose CPU.
I'd really like to back that up, because I don't know if people remember array processors back in the 70s, a specialized piece of equipment. Eventually they disappeared because their function had been subsumed by subsequent hardware. But the whole idea is that you need a specialized piece to develop an idea and work it out. It becomes part of the mainstream later, and then a new requirement shows up in the future. And once again, you're back in the same loop of specialized hardware, figuring out solutions and incorporating them.
Okay,
Yeah,
so we have 1 minute left. If you wanna say something, Kurt, as you know.
Sure, I
concluding.
just summarized real quickly that Silicon Graphics, SGI, is really Systems Graphics Inc. The mantle was passed. NVIDIA has become Silicon Graphics Inc. and has fulfilled Jim's vision. SGI worked out the system level stuff. We worked out the architectures. We worked out how to integrate high performance graphics and high performance compute, and that's our legacy to the industry. And I just want to thank Jim for giving me the opportunity of a lifetime to be a part of it.
Yeah, well, you know what? I can't, honestly, the technology of the company, there are two people in my mind. There are many, of course, including John Montrum, a bunch of people, but Kurt and Tom Jermolek. And I want to point out one time, Kurt came to me one day after we had hired TJ. And he said, Jim, have you spent any time with this guy, Tom Jermolek? And I said, no, not really. And he said, you should. He's super smart. You got to get to know him. And after that, I went off and got to know TJ, and he's to this day my best friend. He and I are in business together, have been now for 15 years investing. And we're today investing together. We have a joint venture capital business of sort. And it's all due to due to Kurt. And I will say, much of the leadership of the overall technical part of the company came from Kurt and TJ.
Wonderful. Well, thank you all so much. It's
Thanks,
really an
guys,
honor.
Thank you guys
moderate
also
this
for giving me
event.
hot machines to get my stuff done with.
And thank you for our building.
You're
It's a
welcome.
beautiful building. Thank
There's
you.
lots of
very much,
stories behind
everybody.
that building, the Bill Graham Amphitheater, but we'll go into that another time.
It's been an honor and a pleasure. Thank you.
All right.
Thank you very much, Mark, and the Computer History Museum.
Thank
Bye.
you, SIGGRAPH and
Bye.
others.